Hi everybody! It is my honor to present our work, Reality Distortion Room, a study of user locomotion responses to spatial augmented reality effects. I'm You-Jin Kim, a PhD candidate at UC Santa Barbara. I had the honor to work with Andy Wilson, Jennifer Jacobs, and Tobias Höllerer in this project. Our project, Reality Distortion Room, is a proof-of-concept augmented reality system that utilizes projection mapping and untethered interactions to study a user locomotion response to visual effects that seamlessly transform the physical room the user is in. We demonstrate the effectiveness of utilizing projected room distortion to influence how users position themselves in the physical space, causing pattern of movement. An increasing number of virtual experiences has started to take the user's physical environment into account. Some VR work specifically addresses the question of allowing navigation in large VR environments in smaller physical environments. These works explored and paved the way for VR redirected walking, but our research marks a step towards a kind of redirected walking in visual augmented reality. Here you see children having fun in cave-like setups similar to spatial AR like ours. The abrupt change in the environment has an effect on how kids move. In our system, the walkable surface is unaltered and intact, and the environment is only distorted outside of the walkable area. Can we still induce a locomotion patterns? We are here to find out. User interacting freely in our system, Reality Distortion Room. The user can easily understand the scale as they watch the transformation occur from the space they are in. As no clear objective or task was given, participants generally assumed that we wanted feedback on the space we designed or testing out the new AR system. Only instruction given was to refrain from sitting down on any surfaces. For our study, we needed a system that can seamlessly blend physical and augmented environment, where the physical layout is presented undistorted. AR headsets such as HoloLens 2 or Magic Leap 2 are equipped with relatively small field of view display limiting immersion. Video pass-through such as the viral XR3 or MetaQuest Pro is becoming more commonplace, but still has some fidelity problem when rendering physical space. We therefore decided to run our study in spatial augmented reality using Microsoft Reality Shader to capture the user locomotion response in the room. Our system offers a full surrounding spatial augmented reality experience using 5 projectors and 4 kinetic sensors. This configuration met the 3 requirements we had, which were to present a fully untethered experience with a wide field of view and appear in a correct size and distance, which our system accomplished. For the virtual room to be precisely aligned with its physical counterpart, the system goes through a calibration process. Static 3D geometry including both stationary and moving object is reconstructed from 3D scans of the environment. As a result, projected content can be precisely aligned with the physical layout, enabling virtual room expansion or distortion as you can see here. There were no tasks assigned to the participants as we mentioned, but we placed particles in the space for them to freely interact with, inducing user movement without providing directional biases. Furniture in the room was highlighted, giving a hologram-like effect. This projection added visibility of physical object in the relatively dark room. The right here shows user locomotion. This example user utilized pretty much the entire floor space without fear of collision. To quantify the effect of each distortion treatment, we measure induced user locomotion, which we categorize into 2 different types, distortion effect and central effect. We define directional effect as the user's movement along a designated axis. And we define the central effect as the change in the user's distance to the center of the room. We design our distortion treatments to maximize these effects. Each distortion treatment is divided into 2 phases, apply and return. In our study, we checked the change of participants' average movement right after 10-second long apply and return segment. During the apply stage, the room shape deviates from the actual physical layout and then it returns to physical room shape and dimensions during the return stage. We analyzed the average movement of the user during the 10-second distortion segment by comparing their position in the room before and after the segment. We tested 20 distortion treatments in our pilot study, 10 to induce directional effect while 10 to induce central effect. However, we found that some of these treatments were not as effective as others. Participants provided feedback indicating that transformation done too quickly or with complicated geometric shapes were difficult to comprehend. Additionally, participants expressed that geometric transformations such as twisting hallways or rotating rooms were hard to understand and causes dizziness. We observed that distortion occurred too quickly makes people stall and move less. With user feedback, we adjusted speed and geometric configuration for the main study. After the pilot study, we decided to only use 5 out of 20 conceived distortion treatment in our main user study with 20 participants. The 5 that we chose are elongation, warp, shift, elevate, and enlarge. As you can see here, elongation, warp, and shift treatments were designed to induce a directional effect, while the elevate and enlarge treatment were designed to induce a central effect. Furthermore, we cross-examined directional effect from distortion effects designed to induce central effect and vice versa, but there were no foreseeable trend found in that regard. On the left, we see the elongation treatment, and on the right is the user's view of the same treatment. The following clip shows a playback visualization of all 20 participants' locomotion in the room from the respective treatment. It should be noted that each user trajectory was gathered separately, one user at a time in the room. The timing is synchronized with respect to the effect to display the user's overall movement response patterns. We believe the elongation movement pattern is caused by participants being curious and getting closer to the extended area, but being pushed back when the elongated wall returns back to line up with the actual wall. Here we see the warp treatment and the user's view. Again, the following clip shows a playback visualization of all participants' locomotion in the room induced by the warp treatment. It is apparent that the user moved to the right side of the room while the treatment is in effect. We believe this pattern is caused by participants moving to the side of the room to better see the end of the curved corridor. Here we see the shift treatment and user's view. Again, here's the overall movement. As you can see, user followed the motion of sliding walls for an overall directional motion pattern. We believe this pattern is caused by participants feeling the need to follow along with the shift in the environment. Here we see the elevation treatment and the user's view. What is shown here is the user's movement in the response to the elevation treatment. As you can see here, users tend to move to the center when room appears to descend, while users tend to spread out from the center of the room when it appears to be elevated. We believe this movement pattern is a result of user traveling to a place that is both safe and has good vantage point in the room. Here we see enlarged treatment and the user's view. And here is the visualization of the overall motion response to the treatment. While the room appears to enlarge, the user walks about the full floor layout, while when the room is being compressed, user tends to congregate in the center part of the room. We believe this movement pattern is caused by user exploring the perceptibly enlarged space and then subsequently the contracted space. Here we provide data points from 20 participants across the 3 distortions that induce directional effect. Each vertical line shows a data point of a participant's average movement made along the directional axis during the 10 seconds of the effect. When there's a distortion treatment, we can clearly see trend in average movement in a particular direction compared to the gray baseline. Results shows that participants' natural locomotion can be influenced by the augmented distortion treatment to significantly induce directional movement, in this case right or left. The shift treatment showed the largest directional effect in our user study. We can also validate that the user position relative to the center of the room can be manipulated with AR distortion, as shown in this figure. The enlarged treatment shows the larger central dispersion and gathering effect in our user study. While two participants shared that the elevation distortion was at times hard to understand, the enlargement distortion ended up being a crowd's favorite, and three participants even asked to experience it again after the study. Most enjoyed the experience, describing it as movie Inception-like experience. Although we had overwhelmingly positive response, we would like to acknowledge that the data was gathered from small pool of 20 participants with limited trial and designs, and further research in this area is needed. Overall, the reality distortion room was successful in inducing users' natural movement in predictable ways. We believe our distortion effect could be used to induce a distance between a physical object and the user when needed. While our work relies on users' understanding of the space through their spatial awareness, our finding is applicable for any future system that could simulate untethered experience with wide field of view. We are especially excited that our method does not require voice or text instruction to move users and provide universal experience in AR environment. Thank you so much for listening to our talk. This exciting research was made possible by the guidance from my mentors, who are also authors on this paper. Please read our paper for details and specifics of each distortion effects.